this particular topic and not a different one. But so I couldn't come up with anything better than saying that I find it's beautiful. Whereas beautiful is of course a vague term. Well, the topic has links to many different areas in mathematics. It's at the interface of very different areas in mathematics. So that's one of the reasons why I find it beautiful. And then I was also reminded of something that the famous English mathematician Godfrey Harold Hardy, the number theorist, in the early 20th century, wrote in his book, A Mathematician's Apology, which is sort of a philosophical reflection on the profession of mathematicians and on mathematics as a whole. So he writes, a mathematician, like a painter or a poet, is a maker of patterns. If his patterns are more permanent than theirs, it is because they are made with ideas. And he goes on saying, so the mathematician's patterns, like the painter's or the poet's, must be beautiful. The ideas, like the colors or the words, must fit together in a harmonious way. Beauty is the first test. There is no permanent place in the world for ugly mathematics. So we see, I hope that this will be a beautiful piece of mathematics for you as well. So the problem I want to start with is the following. It's actually, I think, a problem that was posed by the Soviet mathematician Gelfand. So consider the powers of 2. So 1 is 2 to the 0, right? Pedantic, we should include that. 2, 4, 8, 16, 32, 54, 128, and so forth. 256. And then the leading digits of these numbers. So that is 1, 2, 4, 8, 1, 3, 6, 1, and there will be a 2, and so forth. And then one can ask several questions, and one question one can ask is, does 7 ever occur? Of course, there's nothing special about 7. You could just as well ask, does 1 ever occur? But then the answer would be straightforward, because you see that 1 occurs, 2 occurs, 3 occurs, 4 does occur, 5 will occur once you double 256. So you can ask, does 7 ever occur? And also, more generally, you can ask, with which frequency does each of the digits occur? So if that makes sense, right? So you have to make sense of the meaning of the word frequency to begin with. But you can ask, so with which frequency does each digit, initial leading digit, occur? So the question, anything unclear about the question? I think the question is very elementary, and actually you could answer question 1 just by using a computer, though probably not an ordinary pocket calculator. So I computed that, so the first time, so 7 does occur, so the answer is yes, and 7 occurs for the first time in 2 to the 46th. So you have to wait quite a while till the 7 occurs. So 7 occurs the first time, say as initial digit 2 to the 46. And actually, it'll turn out that each number between 1 and 9 occurs as a leading digit of one of the numbers in the sequence. And also we'll be able to answer question 2, though I'll only sketch the arguments for question 2. So the point is that even without using a computer, you can see that 7 has to occur, and actually each number between 1 and 9 has to occur using some purely geometric and abstract reasoning. So you don't have to use a computer for this. And so one way you can do it is as follows. So let's start with the following remark. So let's try to translate the whole problem into geometry, into a problem of geometry and dynamics. So what is the leading digit? What is the leading digit of, say, 2 to the n? So of course we use the decimal system, so we write numbers to base 10. So the first thing I would like to do is write 2 to the n in a slightly more complicated way, namely as 10 to the n times log 2 to the base 10. So this is this number. And then to get the leading digit, I have to divide by a suitable power of 10 so that I get a number which is between 1 and 10. So I have to divide this, let's say the leading digit k. So I have to divide this number here by ten to the integer part of n log 10 of 2 to the base 10. So this square bracket here is the integer part of a real number, of a number. This you throw away all what comes after the decimal point. So basically the integer part of 1.267 something is just 1. So it's the largest integer, not larger than this number inside the square bracket. If you do this, you get something that is, well, it is a number between 1 and 10, 1 inclusive, 10 excluded, and you still have to take the integer part of this. So this is what you get. So you can rewrite this in the following way. So here you see this is 10 to the, this is actually nothing but the integer part of 10 to the, well, you have to take this number n times log 2 and subtract its integer part. So what you're left with is the fractional part of this logarithm. You get 10 to the fractional part of n 2 to the base 10. It's the integer part of this. And so, so the upshot is this number 2 to the n is k if and only if so the fractional part of n log 2 to the base 10 is in the interval from log k to log k plus 1. Right, because then the number inside the brackets, this one will be between k and k plus 1, so the integer part will be k. Any questions about that? Probably that's not the geometric portion of the argument, so that's some type of piece of algebra. Basically, I need an analytic expression for the leading digit of this number. Okay, so what does that mean? So it means, you can rephrase it as follows. So you consider the unit interval from 0 to 1, 1 excluded. Here's 0, 1. And then you have we have some subinterval of this, which is the subinterval from log 1. So all logarithms are now to base 10 from log 1, which is 0, to log 2. This one. And you have a shorter one which goes from log 2 to log 3. So this is a little shorter. I mean, it doesn't really matter how long it is, but it's shorter. And you have a third one, goes from log 3 to log 4. Still shorter. And so forth. Yes, so finally you have an interval, which is the one from somewhere here from log 9 to log 10, and this is the shortest of all of them. It should be shorter than this one, so it's a very short interval. And so to see what's the initial digit of this number 2 to the n, what you do is you compute n log 2, take its fractional part, and then this will be a number between 0 included and 1 excluded, so it will fall into one of these finitely many intervals. And if it falls into the red one, the initial digit of the number 2 to the n is 1. If this number falls into the yellow interval, then the initial digit is 2. Falls into this orange interval, the initial digit is 3, and so forth. So another way of phrasing it is as follows. So you can say what we are actually doing is we are considering a map, say T, which is a map from this interval to itself, and which takes a number in this interval and maps it to this same number translated by log 2 to the base 10. Right? And then I have to take the fractional part again. This map is basically a translation of this unit interval. It's a translation modulo 1 because I take the fractional part. So I translate, and then everything that sticks out at the other end, basically I translate it back into the unit interval. And so the initial digit to the n is k if the nth iterate of 0 under this map T, this translation map, falls into the subinterval from log k to log k plus 1. Okay. Okay, but the point is, so this interval with endpoints identified is somewhat difficult to imagine. So it's much better to visualize it as a circle. So visualize this interval as, say, curled up into a circle. So I take the interval, take its endpoints, and I just close it up to a circle. So then the picture is something like this, which is not exactly a circle. And these subintervals that I drew there will have their equivalents on the circle. So they get shorter and shorter. I also have a marked point, this point 0 of the north pole of the circle. And then the good thing is that this map T on the circle becomes a rotation, which is much easier to visualize than a translation mod 1. So the map T becomes a rotation. Rotation, say R, but it's the same map. It's just the same map, but now visualized on this curled up interval. Comes a rotation R on this circle. Let's call the circle. So mathematicians like to call circles as 1 because so the S is for sphere and the 1 is for because it's a one-dimensional sphere. So at this point, it's notational overkill, but that's just, that's how circles are traditionally denoted in many parts of mathematics. So we have a rotation. So we have this rotation, R. It's a rotation. And what we have to understand is how the iterates of this marked point 0 up here under this rotation are distributed on this unit circle. So we consider the iterates of this marked point under the map R. So we first apply R, we rotate the point by a certain angle. I mean, I could compute the angle, but I don't worry too much about what it is now. Yeah, so we rotate the point, we rotate again, apply this map again and again, and we get a whole bunch of points. And we're interested in how these points are distributed on the unit circle. And if in the nth step I get a point in, say, in this red segment of the circle, I know, for example, that the initial digit of 2 to the n is 1. So each of these colored intervals tells me what the corresponding initial digit of the number 2 to the n is. So that's the translation. The upshot is we have to understand how the iterates of 0 under this rotation are distributed on the circle. It's basically, so it's a geometric problem because we consider this rotation, and it's also a dynamical problem in the sense that we consider iterates of a fixed map. So we consider how the iterates of this map evolve in discrete time, so to say. Yeah.
So you're mapping K onto that circle thing.
So say it again. Yeah. I just close up the interval. I take this interval and I identify the endpoints, and that gives me this circle.
Okay.
Yeah, and I just transplant these colored intervals to the circle, isometrically basically. They have the same length. It just, imagine that this interval is made up of an unelastic piece of string, and I just curl it up into a circle. That's all. Okay. Any more questions at this point about this translation of the problem into something geometric? So, all right. So there is a second remark. Actually, we won't have to know much about this rotation of our circle. I mean, it's just any old rotation, but so we have to know one additional fact about R, so which we will use in the sequel. So not any rotation will be suitable for the subsequent argument. So this is the only special property of, rather non-special property of R that we'll be using. So no iterate of R is the identity on S1, on the circle. Which basically means you start rotating and you follow what this distinguished point 0 does, and so the statement is it never returns to itself. It's somewhere, but it certainly never returns to exactly itself. And actually this is so this is easier to see in terms of the map T. So it suffices to show this for t. I mean, it's just a different letter. It's just a different way to look at the same map. So what would it mean that an iterate of this t is the identity? So if, say, t to the n was the identity, some n, so that would mean that, that x plus this logarithm of 2, base 10, would have to be x again, at least up to an integer multiple. Up to addition. So say would have to be equal to x, so n times this logarithm would have to be equal to x plus, say, m, where n and m are integers. M and n integers. And because the fractional part of x plus n log 2 would have to be equal to the fractional part of x, and this can only happen if x and x plus n log 2 differ by some integer number. So we see that would mean that that this log would be expressible as the quotient of two integers. So it would be a rational number. So that would mean that this log could be written as the quotient of two integers. Could be a rational number. Two integers. And now, so why is that impossible? So what you can do is you can multiply this equation through by n. So then you get n times log 2 to base 10 as m. And then you get that, so take 10 raised to this power has to be equal to 10 raised to the nth power. So you'd get that 2 to the n would have to be equal to 10 to the n, which is actually 2 to the m times 5 to the n. And this is certainly impossible once you know unique prime factorization. The conclusion would be that you have an integer which which has two different factorizations into prime. So it would be a power of 2, but on the other hand, if m was bigger than 1, then it would also have to be divisible by 5, which is certainly impossible. So this is impossible. Of course, it uses unique prime factorization, which is not altogether trivial, but you see that because of that, no iterate of t or r can be the identity. So really m would have to be equal to 1, and then also m would have to be equal to 0, and then also n would have to be equal to 0, but that's excluded in our assumptions. Okay. So we have a rotation R, and it is such that this distinguished point never returns to itself. And actually no point on the circle ever returns to itself. No power of R is the identity. Questions? Anything? Lost everybody now. Okay. So at least that's the dynamical behavior of this map, right? So it is a rotation, and no power of R is the identity. So now what we can ask is, so how are the iterates of this point 0, or any point on the circle for that matter, how are these iterates distributed on the unit circle? And so the first course assertion that one can make about these iterates uses a version of a famous theorem by Poincaré. It's a famous French mathematician. So the Poincaré recurrence theorem. And the only real drawback about this Poincaré recurrence theorem is that it's much lengthier to state than to prove. So the proof is basically 2 lines. You have to get the formulation right. And you have to realize that something like this is true to begin with. So, so the formulation is a bit, maybe a bit difficult at first, but the proof is completely elementary. And so I'll state it in abstract terms, but we'll apply this then to this very concrete situation of the circle and this rotation R. So if you feel more comfortable, you can always think of the circle and this rotation. So I'll tell you what all the players are in the statement of the theorem in that setup. So so let X, so I'll be a bit vague here, so let X be the space with a reasonable notion of distance defined in it. So that's the only part where I'll be a bit vague, but it's nothing so mysterious. By space, I just mean some set, some aggregate of some objects, which we consider as some unified entity. So just some space. X in that setup is just our circle, some geometric something. So it's just, and there should be some way that we can measure distances between points in that space. So for 2 points, x and y and x, we should be able to say what the distance between x and y is, some positive, at least non-negative real number, and should satisfy some reasonable properties. For example, that the distance from x to y is the same as the distance from y to x. And then if you go in a triangle, then going from x to y and then to z should be at least as long as going directly from x to z, and such things. So just a reasonable notion of distance. So for example, in this case of a circle, you could just take the arc length on the boundary of the circle as a distance. If the points are very close together at least. Actually, this is requiring a bit too much. So we could also do with a space where we only have a certain notion of nearness. But let's take this and then call a subset. So U and X open. So if together with with every point X and U contains all points sufficiently close to X. So this is also not very important. It just means that we single out a class of subsets that is not too pathological. I mean, it's like taking open segments and their unions on the circle. Basically, I take segments on this circle, but without the endpoints. That's nothing very spectacular. And then suppose, so what I also need is, suppose we are given something which I call a measure on open subsets. I call this measure mu, and by this I mean a function a function mu so that assigns to an open U a non-negative real number, mu of U, and such that the measure of some union of opens, so this is a union, is just the sum of the measures of the individual opens if these opens are disjoint. If I are open and disjoint. This, they have no point in common. So you could think of mu. So think of mu as some sort of length, or in three-dimensional space, volume, something like that. So it's like length or volume of these sets. So on the circle here on S1, you could just take the length of a segment, so it's its length, the length of this arc, as the measure of this segment. And now suppose, I promised you the statement was much lengthier than the proof. So suppose you have a map. So you have a 1-1 map, say T, from X to X, which preserves opens and the measure. So open subsets are mapped to opens, and also the measure doesn't change. So, and this is actually the crucial property. So you have a map which preserves opens, open subsets, and the measure. Yeah? Okay, so T of U is again open, U is open, and they have the same measure. Alright, so now and also suppose that the measure of the whole space is finite. Is finite. So then, finally the statement of the theorem. So then, for every open U in X, there is a point, say X in U, and say an integer n bigger than 1, such that T, the nth iterate of T under, so the nth iterate of this point X under T is again in U. So the point is, if you have this setup, so forget about this range property of open, it's just thrown into single out and not two pathological class of subsets, and also simplifies the statement a little bit. Suppose you have such a space. We can talk of distances in it, of nearness, just as in the case of this circle. And suppose you have some sort of notion of measure in it. So in this case of the circle, just arc length. And suppose you have a transformation of the space to itself, which preserves the measure. So in this case, the rotation of the circle preserves arc length. So that's really the crucial property we'll be using. The crucial property of this rotation, it preserves arc length on the circle. And suppose that the measure of the whole space is finite, then for every open, you can find a point in it which returns to this open under a certain iterate of the self-map you're considering. And the proof is very simple. So the proof easily fits on this blackboard. So the point is, so schematically, just suppose, so we have this space here, and this is our space, just a schematic picture of it. We have this subset U open of it, and now we consider the translets of this U under T. So we have another subset, this is T of U, and here's T square U, and so forth. And now because the measure of the space X is finite, two such translets have to intersect at some point. Because they cannot all be disjoint, because otherwise, I mean, the measure of the space would be infinite. Right? Because T is volume, or measure preserving, T of u has the same measure as u. And T square u has the same measure as u. So all these translets or transforms of the initial u have the same measure. So as long as they are disjoint, their measures just will keep adding up and make the measure of the total space x bigger and bigger. Because the measure is fine. So these have to intersect because there's simply not enough space inside x for all these disjoint translets to fit in. So there exists some, say, m and n, say m bigger than n, such that Tn of u and Tm of u intersect. The intersection is not empty. But this means, I can also rewrite this and say this means that Tm minus n, so m is bigger than n, of u has to intersect u, non-trivially. I just apply t to the minus n, so the inverse of t n times to both sides here. So that means that there is some translet under t, so some power of t, some translet of u, which intersects u non-trivially. And so there is a point in u which returns to u. So there is a non-trivial intersection. These two intersect at some point, and so there is a point that returns. Okay. So this is. I'm sorry about the slightly this difficult formulation, but so you can forget about many portions of it. So we don't worry too much about what this openness means, because actually we could also extend the measure to a much larger class of subsets, but I don't want them to be too wild. Alright, so let's apply this. Any questions concerning this weird theorem? It's actually not so weird. It's just the consequence of the fact that there is a self-map of a space which has a suitable notion of measure defined on it, and the fact that the self-map preserves the measure, and the measure of the total space is finite. So translets of some subset which has a certain finite measure have to intersect. So, let's see what I can erase. Okay, so let's apply this to our initial problem. So consequences. Our initial problem. So we have our circle. Here's the point 0, and we have our rotation. So the first, so the first remark is this. So for every, so if I take a very small segment, any segment around this distinguished point 0, so for every small, so arbitrarily small segment, you yellow one in the picture. Around 0. So there exists some natural number such that the iterate of 0 under the rotation is again in there. So such that the nth iterate of 0 under this rotation is again in the segment. It's called the I0. It's again in I0. And so this is just a consequence of, so this follows. Let me just say why. What you could do is you could take a much smaller subsegment of this yellow one, still containing 0, so very, very small. And then Poincare recurrence says there is a point in this subsegment which returns to it under a suitable power of this rotation, under a suitable iterate of this rotation. So if I draw the iterate in blue, this means the iterate has to intersect this very small red segment. But then, you see, the iterate will be entirely inside the yellow segment if this red segment is very, very small. Has to be inside the yellow one entirely. So especially the point 0 is again inside this yellow segment at that point in time. And secondly, if I take an arbitrary segment, so if say I is an arbitrary segment, there also exists some n such that the rotation will map 0 into I. So the nth iterate of this rotation, it will map 0 into this segment. So this means, what this means intuitively is the iterates of the point 0 on the circle are dense. Basically, if you take a very small segment anywhere on the circle, at some point in time you'll find a transform of the initial point 0 under a suitable iterate of this rotation in it. So basically, wherever you look. And so the reason, so this follows from the following observation. So basically we know that there are integers, say m1 and m2, say m1 bigger than m2, such that r of m1 of 0, r to the nth 1 power of 0 is in I0, and the same holds for r to the m2. So rm2 of 0 is also in I0. See, the Poincare recurrence theorem also says that recurrence occurs infinitely often. You could just apply Poincare recurrence theorem to suitable powers of your map. And then you see that a point, in this case 0, has to return to a suitable set, open, infinitely often. So this, from part 1, you know that 0 returns to every small segment I0 around 0, but it also returns infinitely often. So you can find two numbers, m1 and m2, m1 bigger and m2, such that, yeah, you get these two return incidences both of these are not 0. But then you see that R M1 minus M2 of 0, this thing, R M1 minus M2 is a rotation through a very small angle. Very small angle. To a very small angle. Because, you see, of course, it's again a rotation. It's a rotation. It's just rotate. It's a composite of rotations on the circle. And it's a rotation through a very small angle because it maps one point, this one, in this very small interval I0 to another point in this interval I0. So it's a rotation, but it maps this point to another point in there, and we can make this interval I0 arbitrarily small. So it must be a rotation through a very, very small angle, through an angle which we can make as small as possible, as small as we want. And so we see that the iterates of this point 0 fill up the circle densely. Because we found one power of R. This one, which is a rotation through a very small angle. So if we iterate this one, we'll find points on the circle which are very close together. At least as close as we want them. So you see that this implies that 7 does occur. 7 does occur by this abstract reason, just as a consequence of Poincaré's recurrence theorem. Right? 7 does occur. Okay, so my time is almost up. Let me see, maybe can we make 2 comments? Let me conclude with 2 comments. Do you have any questions at this point? Yeah.
What about the second question from the beginning?
Yeah, I'll answer that. Yeah, right away. So, but I don't have enough time to give you all the details, just some sketch. Also notice that, in the second part here, we use that no power of this R is the identity. Because we use that this is a rotation through a very small but non-zero angle. If it was a 0 angle, I mean nothing interesting could happen. So so let me conclude with 2 remarks. The first remark is concerning question 2. So what one can show is that the iterates of this point 0 under R on the circle are actually equidistributed. The iterates of 0 under R are what's called equidistributed on the circle. That's 1. So you could imagine this is saying that if you consider sufficiently many of them, then in the limit, every small segment of the circle will have the percentage of points in it that is given by its length. So every small segment in the circle will have its proper share of iteration points eventually. Or if you make a small red dot, say, whenever there is some point at that point in the iteration, then in the limit, the circle will be uniformly red. So no part of the circle will be redder than any other part. And so this, unfortunately, to prove this uses some Fourier analysis. So this uses some Fourier analysis. And then, so which I can't discuss now. So basically, with some Fourier analysis, one can reduce this. So one can give a criterion, for this equidistribution, and one can just verify that this criterion is satisfied in this case. Binomial computation using complex numbers. So that this implies that the frequency, so with which the digit k occurs is just the length of the segment that corresponds to it, which is log k plus 1 to the base 10 minus log k. So this is just the length of the segment that corresponds to the digit k, right? So I could also write this as log k plus 1 divided by k to the base 10. So this is some frequency, and you see that 1 is the digit that occurs most frequently, 2 occurs already a little less frequently, 3 even less frequently, and so on. So 9 is the most infrequent. And so the second remark, I'll not write that down, but just say a few words about it, is the following. So let me conclude with this. So the Poincare recurrence theorem has some startling physical consequences as well. So this is what I mentioned in the abstract as well. So suppose we have two adjacent compartments or containers, one filled with a gas and the other containing a vacuum, and you have a division or a separating wall between the two compartments, and then you remove the wall. And of course, the gas will start spreading out in both containers evenly. And so Poincare's recurrence theorem actually predicts that at some point in time, so after a certain while, all the gas molecules will again be in the first container. So in the container where they were released from, which is somehow counterintuitive, because you've never observed such a phenomenon in the physical world. And so the explanation for this is that a while could be very much longer than the, say, age of the current universe. So you can calculate what the expected return time would be in simpler cases. For example, suppose you make the following experiment. You have two containers, one of them containing 100 balls with numbers 1 to 100 written on them, just 100 balls, so very few molecules. And you have a hat with slips of paper in it with numbers 1 to 100 written on them. And you draw a slip of paper every second, read the number, take the corresponding ball and place it in the other container. So the container it's not currently in. So you place it in the other container, and then you replace the slip of paper in the hat, and you go on doing this. And then, so Poincare's recurrence theorem predicts that after a certain while, at least with probability 1, all the balls will again be in the first container. And so if you do this every second, the expected return time is 2 to the 100 seconds, which, if I compute it correctly, is approximately a number which is something like the age of the current universe, but squared. So if you do this with a very fast computer, so if a computer plays this game much faster than you could do it, so then I think, the expected return time would still be on the order of magnitude of the age of our universe. So which is, but you could do it with 10 balls. I mean, 10 balls, I think you could do a simulation on it. Okay.